Topic modeling is a cornerstone of natural language processing. Its goal is simple: uncover the latent semantic structure of a massive collection of text without needing labeled data. But as our datasets grow in scale and complexity, we've hit a wall. Traditional probabilistic models like latent Dirichlet allocation, or LDA, require you to predefine the number of topics, and they struggle with streaming data. On the other hand, modern neural topic models offer better coherence, but they are computationally heavy, sensitive to hyperparameters, and suffer from catastrophic forgetting, where the model essentially erases old topics as it learns new ones. Enter COBWEB-TM. This is a new framework for lifelong hierarchical topic modeling that combines the power of pretrained transformer embeddings with an incremental probabilistic concept formation algorithm called COBWEB. To understand why this is a breakthrough, we first have to look at how COBWEB-TM actually works. It operates as a two-step neuro-symbolic process. First, it handles document topic inference. Instead of training a complex neural network from scratch, it uses the latent space of pretrained transformer embeddings, like RoBERTa. It then applies the continuous COBWEB algorithm to partition this space. As documents stream in, the model incrementally builds a semantic hierarchy. It doesn't need to know how many topics exist beforehand, it discovers them on the fly. But how does it decide where a document fits in the hierarchy? It uses a metric called category utility, or CU. In technical terms, COBWEB-TM represents each concept node as a d-dimensional multivariate Gaussian with a diagonal covariance. When a new document embedding arrives, the algorithm performs a top-down search. It calculates the differential entropy of the Gaussian at each node to measure uncertainty. By maximizing category utility, the model favors partitions that reduce feature uncertainty while maintaining enough support. This allows the model to balance intracluster similarity with intercluster separation, effectively deciding whether to insert a document into an existing topic, create a new one, merge two topics, or split a topic into more specific subcategories. Once the hierarchy is built, the second step is topic extraction. To make these clusters interpretable to humans, the model uses class-based TF-IDF, or c-TF-IDF. It treats every node in the tree as a candidate topic, and concatenates all documents in that node's subtree into one large document. It then calculates the importance of words within that topic relative to the rest of the corpus. This gives us a set of descriptive keywords that define the topic. If you need a flat set of topics rather than a tree, COBWEB-TM can actually derive a dynamic flat partition. It does this by identifying a cut through the tree based on a user-defined maximum number of clusters and a leaf ratio threshold. This filters out shallow outliers and groups deep, semantically similar documents into stable clusters that evolve as the data changes. Now let's look at the results. The researchers tested COBWEB-TM against a variety of baselines, including online LDA, lifelong NTM, and various BERTopic pipelines, across datasets like Stack Overflow, Tweet10ER, and spatiotemporal news. The results were impressive. In terms of topic coherence, measured by the CV metric, COBWEB-TM consistently outperformed or remained competitive with the best baselines. But the real win is in stability. Using the adjusted RAND index, or ARI, the model showed near-perfect stability on the Stack Overflow and spatiotemporal news datasets. This means that as new data arrives, the existing topic assignments don't shift wildly. The model is resistant to the drift and catastrophic forgetting that plague neural models. When we look at the hierarchical quality, the results are even more telling. COBWEB-TM achieved the highest scores in parent-child coherence, meaning the child topics are meaningful specializations of their parents. It also maintained high sibling diversity, meaning it can distinguish between two different subtopics under the same parent without them overlapping too much. Qualitatively, this looks like a technology root topic, splitting into coherent subtopics like operating systems or hardware specifications. Because it uses variance estimates over embedding dimensions, it can actually disentangle ambiguous terms. For example, it can tell the difference between a drive in the context of a computer disk and a drive in the context of an automobile, even when the embeddings are close. From a computational perspective, COBWEB-TM is highly efficient. Because it uses a heuristic-guided best-first search, it only updates a logarithmic number of nodes per document insertion. In runtime tests, it remained robust even as the corpus grew to 50,000 documents, while some refit pipelines simply timed out. Of course, there are limitations. The model is dependent on the quality of the pretrained embeddings. If the encoder can't see a semantic distinction, COBWEB-TM won't either. Additionally, since it's an incremental process, the order in which documents arrive can influence the final structure of the tree. Looking forward, the potential for this framework is huge. Since it operates on continuous representations, it could be extended to multimodal topic modeling, incorporating images and audio into a shared hierarchical space. By combining the geometric strengths of transformers with the symbolic logic of probabilistic concept formation, COBWEB-TM provides a scalable, adaptive, and deeply interpretable way to organize the world's streaming information.